Mr. Vincent Lim, our Senior Facilities Manager at NSCC. So Vincent is currently the head of DC at NSCC, providing day-to-day oversight and leadership for our DCs. He has worked in similar capacity with NTT Singapore and CenturyLink, with 22 years of experience in the data center industry. So Vincent has previously worked in ISPire, and as a customer service engineer responsible for crisis management in the Enterprise Nerve Center. He expanded his role in Siemens, Opus IT, New Star, Asia Pacific, while managing multiple data centers at some point. So may I invite Vincent on stage for his presentation on NUS-NSCC i4 DC, a tropical supercomputing DC. Vincent, please.
All right, thank you, Dong Yen. Good morning to all. Welcome to NSCC's soft launch of the Aspire 2A system. My name is Vincent Lim, so I'm the head of the data center for NSCC. So I'm going to talk about a bit on the new data center where the new Aspire 2 system actually sits on. All right, as you know, the system is awarded to HPE. So HPE is the one that is installing it, heterogeneous system, a general purpose system that's used to expand the storage with expanded storage, all right? And we are expecting it to be commissioned soon, all right? So hopefully we'll get to see the system come online. All right, I think this particular site Paul has gone through a bit just now. Just to highlight, we are on the top 500 supercomputer systems. So 199 for the CPU, for the GPU, and 247 for the CPU. So this was actually done. We actually tested it. I'm not going to go into the details of the system because Paul has already gone into. So more on the data center. All right. So this data center is a purpose-built DC, all right? So the power savings for the data center is expected because, as you know, the supercomputer draws a lot of power. We try to make it as efficient as possible, all right? So Paul has mentioned just now there are two different halls. Hall A, where actually there is no air conditioning. I'll explain a bit on that later on when we move on to the next slide. All right, it's a unique design for the tropics, okay, hot ambient temperature, okay, with a dry cooler to cool the system. All right, so we also leverage on Singapore technology. The area B is actually using a rear door heat exchange, all right, so which is developed by CoolLogix using a thermosiphoning system, all right, gas system. All right, digital monitoring, so we actually use a digital twin to build the data center. On top of that, we monitor the data center through IoT sensors. And of course, environmental sustainability, right? This data center is actually awarded the BCA Greenmark Platinum Award, right? So this award normally is given to data centers who have a very low PUE standard, and of course, where there's enough energy savings placed into it, so hence you are awarded this. All right, so as mentioned, it's Singapore's first tropical supercomputing data center. Why we call it that is because besides getting a low PUE, we actually estimate our PUE to be 1.18 based on calculation and computational design. Okay, of course, live data will come in later. Okay, when the system goes online, we will submit our information to BCA for confirmation on our PUE. All right. So IoT, we actually do our own CFD on the system to actually figure out where we are doing right. Okay, and to weed out any hotspots within the area itself. All right, so let's talk about Area A. I think this is where it's unique. Okay, Area A is designed using the tropical data center report that IMDA has actually provided to the public. Right, so based on that, we actually expanded it a bit. Okay, so in area A, this area, there's actually no aircon. There's no cryo unit, there's no air conditioning. All right, the whole area is, the system is being cooled by water to chip, and of course a hybrid of cold plate systems. But on top of that, the area is also being cooled by your normal air within the room. So how do we do this is because the calculated radiant heat is about 24 kilowatts. That's the only 24 kilowatts we need to get rid of. But however, unfortunately in Singapore, even getting rid of 24 kilowatts of heat in tropical environment is not easy. So we have actually put in a series of methods, okay, to make it happen. All right. So area B, this is where, as Paul has mentioned, this is where the the other half of the system sits. Okay. As what Paul has mentioned, unfortunately, this data center we are also sharing it. Okay, it's not only ours. We are sharing it with NUS-AI.SG. So they actually sits at the other side of the data center. We believe in collaboration. No point NSCC hogging one DC. You know, we should share. All right. So the whole area B is using the CoLogic systems, as mentioned. Okay, thermal siphoning. Area B is based on gas base. Okay, there's no water within that particular area. All right, and the area temperature is maintained at 26 degrees. So this effectively tells you that we actually don't need any cryo units within the area. So hence, there is no cryo unit in the area. All right, later on when we talk more about area B, I'll go into more details. All right, so as mentioned, area A is designed using the IMDA Tropical Data Center report. Okay, so how this works is that we look at the equipment that we're going to put in, okay, based on the ASHRAE, the psychrometric chart, okay, of the system. Okay, we can figure out how high a temperature the system can take before it goes into failure. So what we do is that we find a sweet spot and we push the limit, we push the system as much as we can so that we do not expend additional resources or cooling energy on the system itself. All right, so as mentioned, the HP Cray Supercomputer is a liquid cool system, okay, which supports direct liquid cooling, okay, to the chip, okay, and in the bladed system. All right, so the area A hosts 4 Cray EX and 2 CDUs. As Paul mentioned, this is a unique thing. We actually have two CDUs for this particular system is because Singapore is hot, that's one. Okay, the temperature that is running through the system is much higher than most systems that we see. So hence, the second CDU is added in as a additional capacity and as a precaution also to prevent the system from overheating. All right. As I mentioned, we are getting rid of the 24 kilowatts of radiant heat by natural air. All right, so the room temperature is also unique as with the Tropical Data Center report. Since you don't have aircon, the room temperature is expected to be high. But however, our room temperature is running at about 34.5 to 35.4 degrees Celsius. This is how hot it is in the room. Okay, it is purpose-built this way. All right, so one of the reasons why we run it so hot is firstly, okay, we do not want to expend additional energy to cool the room. It's not required. It's a waste of energy. The system is designed to run hot. That's one. All right. Secondly, of course, Singapore has a very high temperature. It's average temperature. So therefore, it's not very effective for us to cool the room down too low, you know, and then after that heat up the room again. You know, so it's a waste of energy. So hence, this is the reason why the Tropical Data Center is designed this way. Okay, of course, in the event that the temperature goes higher, we do have a series of systems to help us reduce the temperature. All right, so in the event that the room temperature hits 35.5, okay, we have an exhaust system that will kick in. All right, this exhaust system will start drawing in cold air from outside. Okay, typical Singapore temperature is about 26 degrees, all the way to, on a hot day, 35 degrees. All right, so in the worst case scenario, 35 degrees, we're still pulling in cooler air, okay, because the room is 35.5, right? So we pull in the cooler air from outside, okay, and exhaust the hot air out into the environment. All right, so this will go on until the temperature in the room drops all the way to 33.5. That's where the exhaust system will close. Of course, the other issue we have is humidity here. In Singapore, it's humid, okay? So the moment we open up, we're pulling in humidity in also. But however, we don't have much of an issue because firstly, the room is hot. Let's talk about the room humidity on the average. The room humidity on normal operating average is about 40% humidity. So that's relatively quite good. It's already a computer room humidity already. So even if we pull in humid air from outside when we do the heat exchange, it goes up at a maximum of about 20. So you're looking at about 60 humidity, which is still good at the current moment. Worst case scenario, in the event it's raining, okay, we do have 2 dehumidifiers in the room. This is an extreme case, okay. If let's say we do pull in more humidity than required, the dehumidifier will kick in, and then after that it will dehumidify the room. But of course that will also mean that it's a chicken and egg thing. When you dehumidify, it means you heat up the room, but you're trying to get rid of temperature. So that's where we have to find a balance. To be honest, the system can operate all the way up to 40 degrees. Hence, we start exhausting at 35.5. Why? Because for the dehumidifier to bring down by 10%, the temperature goes up by 2 degrees. So therefore, 39.5 gives me a good 20% of the humidity that I can get rid of before my room starts to overheat. So this is the design of the room. So that's how we take care of the temperature and the humidity within this particular room. All right? So now we talk a bit about the cray system. So there are 2 internal loops that's running. Okay, one is within the cray itself. Okay, the liquid cooling. Now the temperature within the liquid cooling is about 40 to 45 degrees. The what we call the into the system is about 40 degrees. The output from the system is about 45 degrees. So then it goes in the CDU, okay, your cooling distribution unit, where it does the heat exchange. All right, then it does the heat exchange with a second internal loop, which goes to the dry cooler. Now this dry cooler internal loop the temperature is much lower. You're looking at about 35 roughly going in. Then of course coming out, the temperature will be higher, almost 40, because it does the heat exchange with the CDU itself. Now this dry cooler works in Singapore because typically, even if the temperature of the water that goes out into the system is about 40 degrees, Singapore rarely hits 40 degrees. So as long as we have enough delta T, okay, the temperature, the water in the system will cool down, and hence we save on cooling in this sense. Because let's be very honest, running a supercomputer is going to be very power intensive. Is cooling intensive. So we are trying to reduce our operating as much as possible so that we can provide with the users a value for money system. All right? So there's a bit inside of what the CRAX looks like, and of course of the CDU unit. The inside where it does the heat exchange, and of course how one of the knots look like. All right? So now let's talk about area B. All right, so area B is same thing, okay, it has no aircon. Surprisingly, we can get rid of CRA units. Okay, the only aircon that there is an FCU, okay, to provide positive pressure to the room, to allow the dust not to come in the moment you open the door. Hence the positive pressure. Of course, in the event that there's human in the room, okay, so having an FCU, there's airflow. So at least the human inside can survive. All right? So the room is designed to maintain at 26 degrees. All right? So it's slightly higher than what our Singapore government has proposed, 25 degrees. We're pushing it to 26 because we actually done our calculation. 26 is the best for the system. Why we are saying that is because of the CoolLogic's rear door cooling. The CoolLogic's rear door cooling itself acts as a cooling system for the whole room. Later on, I'll explain why. All right, it uses a thermal siphoning method using the gas instead of liquid. So using gas has its advantage because that means that within the whole area B, there's no water. You eliminate the risk of water ingress. All right, and as we all know, computer system hates water. The moment it touches water, we have more problems. Right, so hence this was used. All right, so most of the rear door that you see are designed this way. Okay, but however, the CoolLogic system is designed with a shared hot aisle system. Right, so what this means is that instead of one rear door cooling one rack instead, all the rear doors help cool the whole row instead. So it becomes a shared cooling. So for example, if let's say one row can take up 200 kilowatts of energy, so that is shared amount. That means it doesn't mean that each rack has to be 20, it can be 15, then the another rack can be 35. Then you just make the appropriate adjustment within the racks. So this gives the advantage of flexibility. You may not want to spread it. You may want to put some high density machines in certain racks. So this is where we get the advantage because it's shared. All right? So of course, in the event that you do not use as much, you don't need to use one whole row of 200 kilowatts. It is possible for you to remove, based on design, some of the doors may be just blanking panels instead. So you reduce the amount of rear door that you have because each rear door takes away about 20 kilowatts. So it really depends on what do you need. So this gives us a flexibility. All right. So hence lower capex. Okay, in terms of the HRS system. So this is an actual photo of area B that we actually installed the system. All right. So a bit on the design. Okay, so as I mentioned, all the servers taking the air from cold air into the rack. Okay, takes away the heat, comes out, goes through the rear door, comes out as cold air. All right. So the gas goes in from this way, from the bottom, gets heated up, gets vaporized, goes back to the condenser, and after that, okay, it gets cooled down by the chill water from the building and comes back in as a liquid. So this is a self-generating system. So that you will notice there's no pumps at all, right? Purely by buoyancy and gravity. Okay, we don't use any pumps at all. All right, so a bit more on how this is. So because it's a closed loop system, no fluid loss, okay, no contamination, there's no risk of contamination. All right, everything is closed within the system. Liquid gas goes in, gets heated up, vaporized, goes here, gets cooled by the chill water and condenses back. Right, so as I mentioned, we kept it at 26 degrees because why? We did a CFD. This is the best temperature to run the system. So if you notice, this design is also a bit different from most data center. Most data center use a front, back system so that they can do what we call aisle containment system. But if you notice, in this particular case, we don't. We use front, back. Why we do this is because the cold air comes in from the front, goes into the racks, gets heated up, comes out into the shared cooling chamber, gets cooled by the rear door. By the time it comes out, it's aircon temperature. You're looking at the temperature of about 24 to 26 degrees. All right? So hence the reason why we designed this way, and all the rear door behind actually has variable speed fans, okay, that actually sucks the air from the inside of the rack out, okay, and then after that while it's doing that, it's also throwing the cold air into the next rack. So it gets thrown into this rack, and the cycle continues. So hence, the design of this is done this way. All right? One direction. All right? So, well, why are we using this is because this is also done in conjunction with A-Star. All right? So they actually did a life cycle environmental and cost assessment of this particular system. We've looked at the report. We like what it says, 40% lower in terms of cost. All right? I think nobody will reject a 40% lower cost. So hence, that's one of the reasons why we are using this. All right? So that's all I have for you guys. So any questions?
Thank you, Vincent. So we can take one question now, and can we show the Slido QR code?
Do we have any questions?
So the QR code will be valid for the whole day, just for the tech session. So I think there are two questions. I'm not sure whether they are directed to Paul or Vincent, but
all right.
Both the questions are asking about the location of Aspire 2A. I think, yeah.
All right. So as mentioned, location of Aspire 2A is inside NUS I4 Innovation Center. All right. So it's currently located there because we are working with NUS in collaboration to build this site. As I mentioned just now, the site is shared between us and AI.SG. So, of course, it is open also to the internal tenants of the Innovation Center. So those tenants are actually given first rights to host their system there together with us.
Okay, thank you.
All right, thank you.
Yeah. Thank you, Vincent. Oh, sorry, Vincent, is there one more question? Can you answer one more question? Sorry. How long would you expect for area A to sustain more than 35.5 degrees at any time?
How long do we expect area A to sustain 35.5 at any time?
More than 35.5.
More than 35.5. Actually, none. As much as possible. Because what happens, the moment it hits 35.5, okay, the exhaust system will kick in. The temperature will start dropping. The exhaust system will start pushing out the hot air and start pulling in the cold air from outside. So effectively, whenever the exhaust system turns on, it stays at 35.5 for a very short period, maybe less than a minute, and you start seeing a drop. But however, of course, a small drop is useless to us. We need at least a 2 degrees drop before we shut off the system so that it gives enough time for the heat to build up again, if necessary. All right, and of course, it gives enough leeway for us to play around with in the event that the temperature doesn't go up, but that's very rare. So far, we have been testing the system for the past 4 months, right? Since the system came in. We run a full load test. We have no issue getting rid of the temperature at the moment. So far, we have not encountered any. The system is working. I hope that answers the question.
Okay. Thank you, Vincent.
All right, thank you.